Speaking of easing back into lecture mode, though, let's talk about this stuff. So far as we have been seeing things, right, we've had a small variety of forces that we have dealt with, right? We said, okay, well, gravity is a big one. Then we've got things like the normal force. If you've got ropes, you might have tension. If two things are rubbing up against each other, there's probably going to be friction. And we kind of left it at that, and maybe thrust. Thrust sometimes, right, for rockets, because for whatever reason, you know, we're like, okay, you know, what are simple things to deal with? Blocks on slopes, sliding something across the floor, rocket science, you know, those things, all grouped together. And I know I said together twice in a row there, but the whole point of that is that we are primarily dealing with one object at a time, and we were thinking about only its motion along one single direction, right? Whether or not we really talked about it in that sense, it really was acceleration along one direction. The other forces, the other directions along those forces would just cancel out to be zero. So today, we get a little bit crazy with it, and we bring in what happens when you have a second object, right? And that's what Newton's third law is all about. And speaking of that, does anybody actually know what Newton's third law is before I dive into this all the way? Does anybody remember what this one was? This is like the big one, the most popular one. Or am I asking for too much for... Yeah, equal and opposite. I was going to say, I might be asking for a little bit too much participation right after an exam. Equal and opposite reaction, that is the short sum of it. So those first two, right, just in case. Newton's first law is an object at rest will remain at rest. An object in motion will remain in motion. To change that motion requires some force. The second law is that force, right? It is our definition of what force is. F is equal to ma, or specifically if you want to look at F net. But let's think about this real quick. Before I go into this and give a formal definition, think about something here. Blocks with masses 1 kilogram, 2 kilogram, 3 kilogram, right, kind of sized accordingly here, are lined up in a row on a frictionless table. No friction to worry about or anything else like that. All three are pushed forward by a 12 Newton force applied to the 1 kilogram block, right? Kind of exactly as we've got shown in this picture. So you might question, okay, well, how much force does the 2 kilogram block exert on the 3 kilogram block? That's a little bit of a difficult one to answer right now. 1 kilogram on 2 kilogram, that's a little bit difficult to answer right now. Can anyone tell me what is the acceleration of all three of these things together, though? I'm going quick maths here. 2. That's exactly what I'm thinking here. And why am I thinking like that? Well, what's the difference if these things are 3 individual blocks, or if I have a mini staircase instead? Let's blur the lines here. Let's kind of say, hey, let's imagine that this is all one big object together with 6 kilograms of mass. If the whole thing as a strange-shaped block has 6 kilograms of mass and I have 12 newtons of force, I'd expect an acceleration of 2. Just so, if I were to saw through my weird staircase object, and what I am left with is... Where's my eraser? Do they not have my... They don't have my draw tab up here anymore. Please, thank you. Let's imagine, though, that I sawed through that staircase, and now I've got 3 distinct blocks. I don't think anything should change. Right now, of course, I've got 3 blocks pushing on each other, but that's kind of internal stuff, right? The whole thing still moves with 2 meters per second squared acceleration. So, all of this is going to be determined by Newton's third law, and you guys have it already, I think. But every force occurs as one member of an action-reaction pair of forces. That's kind of a, it's a wordy definition and everything else, but what it's saying is that for every single force, there is another force going exactly the other way. And we talked about this a long time ago when I first brought up stuff like the normal force. When I lean into the wall and I push into the wall, I exert a force on the wall. The wall, in turn, exerts a force back on me, and that's what happens. right? If you sit on your chair, you exert a force on your chair exerts a force on you. That's why, generally speaking, like when somebody sits on you or something else like that, you feel that extra added weight. They're exerting a force on you, you exert a force on them. This happens whether or not we are looking at things like contact forces, so normal force, for example, or friction, or anything else like that, or gravity works in exactly the same way. Right? As it turns out, the Earth is pulling on you with a certain amount of force, and you are pulling on Earth with that exact same amount of force. So think about all of the force that the Earth is exerting on you right now. You're pulling that much on Earth as well. Why doesn't Earth care about that? Why doesn't Earth move that much? And yet Earth's pretty big, right? It's like, I don't know, more than 10. It's pretty large. So comparatively here, if it's the same amount of force, it's not going to be the same amount of acceleration because Earth has so much more mass comparatively. So that's our big thing. If I have two objects and they're exerting forces, they're going to be exactly equal in magnitude but opposite in direction. That is, we go back to this picture. We zoom in if we would like to, if we want to get really crazy with it. Let's Control-Shift. Which one is... My zoom in buttons don't work? Okay, that's fine. I'll just do this manually. That means between 1 and 2, there is a force on 1 from 2. There is a force on 2 from 1. There's a force on 2 from 3. There's a force on 3 from 2. And I know what I just said was a weird turn of words and everything else, but this is when the blocks are pushing up against each other, they're pushing up against each other. Right? That's really what we're going for. A push is a force. I know those two things push against each other because that's what I'm used to doing in my everyday life. I push things around. So, try this with a concept check real fast. Got most of that on the screen again. Something like that. A mosquito runs head-on into a truck. What is true during the collision? What do we think? We got a lot of options here. Take a minute to read through these. Think about them. And I want to be technically true here. Right? I want to be very, very, very technically true. Not, you know, is the typo of the truck accelerates. I don't see a typo anywhere. But the mosquito does not. I'm not gonna have... Nobody feels bad about a mosquito. Somebody would feel bad about a goose. Let's be real. Come on. Somebody would. Okay, so what we're thinking about here. Both of these things, right? When they come in contact, mosquito is in contact with the truck. There is a force between the two. That force, by Newton's third law, is equal and opposite. So whatever force the truck exerts on the mosquito is also going to exert on the truck. The difference here, though, is that a mosquito has a mass of micrograms? I honestly don't even know. Mosquitoes are very tiny, though, right? Compared to a truck, which I'm going to guess is somewhere around 2,000 kilograms. That sheer difference in mass, many orders of magnitude of difference in mass, means that the same force will be felt very differently. The magnitude of the mosquito's acceleration is going to be significantly larger than the acceleration felt from the truck, even though the force felt by each is exactly the same. Does that make sense, or do we have any questions on that one? Yes, so the force between the two. So if we're thinking about the force from Newton's third law here, what we would have is that, I've got my mosquito, I've got the truck. Something like this. The force between the two is going to be exactly the same. Force is equal to the other force, at least in magnitude. So the force on the mosquito is the same as the force on the truck because they are colliding in contact. That's exactly what Newton's third law is going to tell us here. But because F is equal to ma, this is where the individual masses will come in between the two. The mass of the truck is somewhere around 2,000 kilograms. So even though it's the exact same force, that's not Newton's second law. What am I writing? I meant to write this as acceleration is equal to F over A. Doing it again. F, there we go. Something or another. That's what we're trying to write out. I'm going to focus on, I don't know. Watch my waving hands. That's going to be the answer here. The acceleration of each one is really what we're talking about in all 5 of these choices. So even if it is the same force between the two, the fact that the mosquito is micrograms, or at least milligrams, many orders of magnitude smaller than the truck, means that even if the force is the same, the mosquito is going to feel that much, much greater acceleration. Yeah, and if you compare this to think about what happens if anybody has been driving through those bug swarms or anything else, right? Your car does not notice the bug swarm, right? I would argue I can't see any sort of real difference in my speed when I fly through a bug swarm or anything else like that. My windshield gets all blocked up. But the bugs certainly felt a change in their motion. I'm not driving through a flock of geese. And everyone knows there's a loving relationship between geese and trucks. Right? You've seen the Courage episode, right? Okay. But anyways, when we're talking about solving these problems now, what we're going to be doing now is we're adding this extra little step where essentially we're saying, okay, well, now that we've got more objects, if we have more objects, we need more free body diagrams. So when you're going through these things, you're just going to draw a free body diagram for every single object you've got. That's really the only step that we need to add here. And we need to remember that Newton's third law is going to be a big deal for us at this point. So let's try something here. Let's take this. Let's see what we've got in this picture. I've got block A is heavier than block B, so it wants to slide down. All surfaces have friction. All surfaces have friction. The rope is massless, and it doesn't make any significant difference for the rope or anything else. The pulley doesn't matter. Frictionless bearings, so there's no energy lost because of that. But with the ropes where they are, with the blocks where they are, I want you guys to draw out 2 free body diagrams and connect some of the forces that you think should be linked together. And let me think about this real fast. I would expect, for example, when I'm looking at something like block B, I'm expecting, I think, 4 forces here. So that's my hint. I want to make sure that I'm actually correct with that. Yes. 4 forces on B, there are more on A. Take a few minutes, though. Work on this one. See what you can come up with. And then we'll chat about it and make sure that we've actually got everything accounted for. All right. So I want to see what we got, and let's talk about all these things. B is going to be the easier one to actually look at here. Let's go ahead and draw this thing out first. Oh, and for anyone that didn't have it before, you've got a little badge. If you'd like to take your screen grab of this right now or anything else and wear this around, I don't know, make it your screensaver or something else like that. I can go back to it at the very end if anybody really feels strongly about it. But let me go ahead and draw this thing out. Let's draw the picture exactly as we see it first. And that way we've got a good sense of what this thing is going to look like. Block A, block B. Not the worst drawing in the world. Something like that, something like that. And we'll put a circle right here. That almost worked. You know what? That's good enough. Something like this. Perfect, right? All that stuff. You know, it was good until that point. So we have block A is going to be the one that's actually sliding us down. We've got block B right here, all of that good stuff. Let me draw like my little dotted line here so that we know, hey, this is where this thing wants to move. Or even better yet, let's do that as acceleration. We say, we know there's an acceleration pointing this way. What does that mean about the motion of B? What way is B going? Is it going anywhere? Yeah, B's sliding up the slope. If A is going down, there's this really fun feature of ropes, in that the length of the rope, unless you're dealing with elastic, and that's a completely different story, the length of a rope doesn't change, right? Or a chain or anything else like that. For the most part, they're going to hold the same length. If I pull on one end, the other end has to give, right? There's no way to go back through that any other way. So I know that B has to be accelerating up like that, and that just helps me clear up my picture a little bit more, get a good understanding of what's going on. So let me think about this now. Let me split these things up into two individual pictures, because on its own, if I try to draw every force right here, it's going to get real messy real fast. And this is a circumstance where when you're thinking about those free body dot diagrams and everything else, yeah, they get a little bit more use at this point. They get a little bit more consideration for what we've got going on. But anyways, I'm going to start here with B. So B is kind of sitting on A, right? So the slope, as I see it right here, this is actually A down in this area, but we're not going to worry about that quite yet. If I think about a block on a slope that has some friction and an acceleration going like this, think through these things piece by piece. I say, okay, well, that's the way that it wants to move. So friction has to be pulling backwards on that. Let me call this friction of B. Friction of B. I'm going to use a normal force. I'm going to use this as capital N right now. I know I like to use F of N a lot of the time, but this just makes it a little bit easier that I can say N of B. Okay, so far so good. There is gravity pulling down on this thing, so let's call this, let's do MBG. That'll work for me. And then finally, we've got the tension of the rope pulling up like this. So these are all my forces. Those are the four forces that I'm expecting on B. Any surprises, anything crazy, critical, or anything else like this so far? Do we feel all right on this picture? All right. And I bring that up because our next picture here is about to get a little bit more wonky. There's some more stuff going on with this one. So a lot of the time what I like to do with these things is that I don't necessarily... Is there a force of A on B? Yes, there is. What is that force? I have it labeled. It is indeed the normal force. It's not the slope providing the normal force, but block A is the one providing the normal force. So sometimes I like to draw these like little spots right here to say, hey, don't forget, like I'm focused on block A, but there is something going on right here, right? That's why I've got like the very bottom half of block B kind of in focus at this point. So then, let's start with that one. If block A has to push up on block B to give it that normal force, then surely block B has to push back on block A with exactly equal but opposite force. So that's going into the slope. Now, I can imagine a couple other things. Of course, A is going to have its own force from gravity. It also is going to be in contact with the slope down below. It is also going to be experiencing another normal force, and that is what I'll call the normal force on A. This is the force coming from the slope, acting on A, pushing back against it. I have a rope attached this way, so there's going to be a tension just like this. I also have friction pulling me back this way. Call this friction of A, and that's the friction between the slope and the block. But there is one more force that I have not yet considered, and what is that force? Friction of B on A, exactly. There is a friction force on B between the surfaces of blocks A and B. That means that there so too must be a friction force on A between A and B. So what I'm going to do then is I'm going to write it, it's going to look something like this. it is going to be pointing in the opposite direction because it's going to be an equal but opposite force, right? And that's exactly what happens, right? If one hand, again, I go back to this description of pressing my hands together, moving these things back and forth, right? The friction opposing my right hand sliding up is the same friction force that's going to be hitting my left hand as well. They both feel that same friction force, but pointing in opposite directions. So that's it. 1, 2, 3, 4, 5, 6 different forces acting on block A. So this is where we get some extra complication, and this is where it's very easy to miss some of these small details because there are a lot of things going on. Right? Keep in mind, you got to look at every single point that there is contact between two objects. Because you need to determine, okay, well, I see contact. I know there's going to be a normal force at a minimum. But then I need to also ask, is there going to be friction? FA and FB are both pointing in the same direction because, for one, friction always opposes motion. That's our big part of it so far. But on top of that, we derived F of B coming from this picture right here. Right, that's essentially we said, okay, well, we know that there's friction opposing motion on block B. So if that is coming from block A, then block A must similarly be experiencing that exact same friction force, but pointing in the opposite direction, equal and opposite. So if we wanted to now, there's the whole drawing the dotted lines and everything else, and I don't think that's necessarily a bad idea. But it can make my pictures a little bit more messy sometimes. So, you know, I might have something like a... Right, it just gets a little bit messy sometimes. Sometimes I like to do that and everything else, but most of the time I just like to be careful with my labels. So there is no into the subscripts that you can do either. I could have written this out, you know, my gravitational forces could have been something like F of G, B, you know, F of G, A. I could do all sorts of things with these if I wanted to. But yeah, would you draw a dotted line for the tensions? Yes. Yes, I probably would. And our picture gets a little bit crazier. Tension is always one of the ones that I get a little bit funky with sometimes. I think it's probably good practice to do that. Yes, I think that's probably good practice. We don't need to talk about when that's going to get crazy quite yet. But later on, in a few more chapters, I'm trying to remember exactly what chapter it is. In a few more chapters, we get into some, maybe like quite a few more chapters, actually. Not momentum, not impulse. Going to be chapter 12. In chapter 12, we're going to make that a little bit messier. Tension doesn't always have to be equal, but for all of our stuff right now, it will be. So yeah, dotted lines, you know, I'm so-so on them. Sometimes they're good for connecting ideas, but most of the time I just like to think about it in labels, and I like to describe these things. You could also do something, if the dotted lines are a little bit messy on your pictures, what you could also say is you could have like a column of shared forces. This is what I'll do sometimes as well. Shared forces, the forces that show up in both pictures would be stuff like the normal from B, the friction on B, and the tension. Forces that show up in each side. Okay, so we go back to this picture here. And I want to kind of bring up that idea again. If I said, you know, my advice here is that every single time you've got contact between two surfaces, two objects, you need to be determining first, you know there's going to be a normal force. Second, is there going to be friction? Is there going to be friction between mass 1 and mass 2? What do we think? Ooh, that's a strong yes, but I don't think I would agree. I'm going to say no, but why? Yeah, they're not moving relative to each other. Right? If mass 1 and mass 2 are trying to slide against each other, then I would say absolutely, friction should be there. But they're stuck together, right? I said it's not really any different. If this had been one big staircase-shaped object all together, instead of 3 individual objects, I wouldn't tell a difference. I wouldn't know. these could be glued together and I would never know because I'm just going to push this thing and the whole thing's going to move. The fact that they are separate pieces does not change their motion. It just means there's some internal forces going on. And realistically, if you want to get really crazy with it, so too is true when I push on the wall or anything else like that, right? The wall has all of the atoms pushing on each other. It gets complicated. But for the most part, what we're looking at here is that when two objects are moving against each other in some way, that's when we're going to have friction. Otherwise, if they're just stuck together and moving together, I'm not expecting there to be much friction. Use a little bit of discretion on that one, though. Think about, describe how things are moving. Should there be a static friction or anything else like that? You've got to think about those things. You've got to consider what would be happening. Consider these things. How can I change these things if I pushed it from this side or anything else like that? You all have, a good number of years of life experience at this point. You have moved some things around. Think about what happens when you move those things around. Tie that experience in with all these physics problems because it works very well. But I do actually want to solve this out. I want to see if we can do this one. Because this is a good one to take a look at here. How much force does the 2 kilogram block exert on the 3 kilogram block? Does anybody have a good answer? Does anybody know the approach? Or do we want to look at this for a minute or two? Let's look at it for a minute or two. Let's say the next 1 or 2 minutes, I want you to take a look at this thing, see if we can answer at least part A. Think about what we said before when we first looked at this picture, and think about what we have just talked about now in the last problem. But take a couple minutes, see if you can come up with an answer here. Okay. And I don't even need to necessarily move away from this. But here's what I'm thinking here. I know what the acceleration looks like at this point. We said before, we can imagine, because it's all moving together, as if it is one big object just kind of sliding across the side. That means that the acceleration of block 1 is known, the acceleration of block 2 is known, the acceleration of block 3 is known. If this was one big 6 kilogram object, and it had 12 newtons of force acting on it, I would expect acceleration of 2 meters per second squared, saw the 6 kilogram block into 3 pieces, same acceleration. There's no real difference here. But now we have to look at this thing individually. We say, okay, well, what's going on with M3, for example? Well, I know there's a normal force. I know there's a gravitational force. Those are going to cancel out, and since this is frictionless, I really don't care what happens in that axis. The only force in the x direction on block 3, though, the one that we actually care about right now, and let's go ahead and I'll even highlight this thing orange so we can get really crazy with it. That kind of shows up better. We want to try and say, hey, we are working with this one specifically. The only force acting on this thing right now that is going to be doing anything is going to be the force of 2 on 3. Call it force 2-3. Force 2-3 is what's providing that acceleration. That is, if we know the acceleration and we know the mass of the object, that's equal to force 2-3. That is, 2 times 3, force 2-3 should be 6 newtons of force. Now, I can do the exact same thing with 1 and 2. What I can say is that if I look at block 1 specifically, and this is going to get a little bit funkier, so let's do this one in green, for example. Let's highlight this in green so we can get a good view of this thing. This one right here is going to be a little bit funky because I have my 12 newtons of force pushing me one way, but then at the same time, block 2 pushes back on block 1. So I'm going to be expecting a similar force coming out like this. Call it F21. So that is 12 newtons minus F21 should equal mass 1 times A. The mass is 1 kilogram. The acceleration is 2. So we have 12 minus something is equal to 2. And I know my arithmetic skills have not been up to par lately, but I'm still willing to bet F21 should give me 10 newtons. Does that make any sense? Sure. 6 newtons, I know what the acceleration should be. I pretended as if the entire object, or all 3 of these together, were one big object. Because I say, okay, I see this whole thing is moving. If I see this whole thing is moving, and I know that if I were to sum up everything, I would have 6 kilograms, 12 newtons acting on that, I should get an acceleration of 2 meters per second squared. That is, every individual piece has the exact same acceleration of 2. Then I have to look at these blocks, and I have to say, okay, well, let me take a look at the forces actually acting upon them. Block 3 has 3 different forces. I've got a normal force pointing up, I've got gravitational force pointing down. Those 2 cancel out. So I've kind of removed them from the picture just so it's not cluttering up everything. Those 2 cancel out and don't do anything for me. Block 2 pushes on block 3. That's what I've got as my F23 force. The force from 2 on 3. The force from 2 on 3 is my net force, essentially, right? There's no other forces to cancel that one out, so the net force on block 3 should be equal to the acceleration times the mass of block 3. I've got 2 times 3 should give me my 6 newtons of force needed to get that the acceleration of 2. Does that make any more sense? Perfect. Then for block 1, we do essentially the exact same thing. We say, okay, well, there's a force between 2 and 1, but there are now 2 forces acting on block 1, right? There's my 12 newtons coming in, and then there is the pushback from block 2. So I've got my 12 newtons to the right here, and then I've got my pushback from block 2 right there. I know that should be equal to my net force of block 1. Call it F net. M1 times A. M1 times A, I'm going to have 1 kilogram times my 2 meters per second squared. The result should give me that F21 has to be 10 newtons. Right. So, concept check for everyone here. Let's imagine. The top block is accelerated across a frictionless table by the falling mass lowercase m. The string is massless. The pulley is massless, frictionless. We're not losing anything. Tension is the same on both ends of this. What is the tension in the string? I know this thing is falling. I know that there is an acceleration going like this and an acceleration going like this. Think about the forces on my hanging block. I don't have a lot going on here. I've got just gravitational force pulling me down. I've got tension pulling me up. I don't know what quantity tension actually is, but I do know that the block is accelerating, which means F net is equal to MA, which is not 0, is equal to, so I've called this direction downwards positive, so let's stick with that. I said FG is going in the direction of my acceleration. Tension opposes that. If my acceleration was 0, then I would agree. Tension would equal to mg. But here, what we're basically saying is that gravity is overtaking tension. Gravity is pulling down. Tension is not enough to stop the motion of the block that's hanging over the edge. And that tension right there is the same as this tension right here, right? Because that's how ropes work. But all I really need to do is look at my bottom block here to say, hey, this thing is falling. There is an acceleration to this block, which means tension and gravity cannot be equal. B is right out. The block is moving downwards, though, and if the block is moving downwards, then tension is not as strong as gravity. Gravity is winning that battle. Tension is less than gravity. This is the one that we're looking for. Check mark, circle, everything else. Yeah, we had a lot of answers in that one, but this is kind of like the perfect rounds to talk about this and everything else. So let's imagine some other scenario. Whatever's going on with the top block, right? If we are pulling this thing up, then what would we say about tension versus gravity? If the hanging block was traveling upwards, then tension would be greater than gravity. Right? Tension is kind of like the normal force in that we don't necessarily know what it is. It's some variable force in between two other things. We have to know what's going on with the other pieces that are known. Gravity is always going to be gravity, right? It's always going to be m times g. That's not going to change. Friction is kind of variable, but it's always its own set equation. Tension and the normal force are those forces that are just there as much as they need to be. And I guess static friction kind of falls in there in the same category, right? Kinetic friction is the one that we definitely know what the expression is. But like a normal force, remember that the normal force, the more I push on the wall, the more the wall pushes back on me. Tension, same deal. The more I pull on one end, that's going to be increasing the tension of the rope. So, speaking of all of this, I've got a problem for you all. Let's imagine the sled dog in the figure is not just a good boy, he is dragging both of these sleds through the snow, right? He's good and working. Got a very important job. Let's say that the coefficient of friction between the sleds and the snow is 0.1. So we do have friction here. If the tension in rope 1 is 150 newtons, what is the tension in rope 2? So what you absolutely 1000% need to do is draw out two free body diagrams. A free body diagram for sled A, a free body diagram for sled B. We've got a small variety of forces acting on each of these. You need to label all of those forces. You need to think about what's going on with the acceleration. Is the acceleration the same or different between the two sleds? And then you can use that to solve out for tension 2. I'm going to say let's take the next 5 or 6 minutes on this one. Take a good solid look at this, work through it a little bit. Those free body diagrams are very, very important. But let's do that for a little while, and then we'll come back and check what you've all got. All right, and let's start taking a look at this thing. And yeah, for some people, if you're using the dot free body diagram style and that works better, more power to you, right? I mean, it is what's recommended in the book. Some people do recommend it. I don't like it quite as much personally. I think it kind of abstracts me from the problem a little bit more than I'd like. Sometimes I miss some things for it, but if it works for you, I mean, everybody's got their own style with everything. So more power to you, right? I'm not going to say that anything is wrong. It's just not the style that I use. But as long as we can all agree at the end of the day what we're looking at and everything else, then, I'm perfectly happy with all that stuff. So let's do this in like a blue color so that we're like, okay, that's snow, of course, or ice or something. I don't know. We will have sled 1. We will have sled 2. And we will have the dog. It's got a tail and a head. Dog, right? So, more importantly, though, I'm mostly focused on these two blocks, right? The dog is kind of a fun thing here, but I'm not really concerned about what's going on with that thing. Instead, I want to think about what goes on with each of these blocks. So let me make sure that I've got these things right. The left one is A, and we've got some masses for these things as well. So mass A is, and I've immediately forgotten 80 and 100, but it's 100 in the back, 80 in the front. 100 kilograms. We also have that mass B is 80 kilograms, and I've got my my given column started here, right, if you can't tell. We know that the tension in rope 1 connecting these two sleds is going to be 150 newtons. So call that T1. T1 is equal to 150. And let's go ahead and draw these ropes out while we're here thinking about these things. Draw kind of like, oh, I thought that was going to be a straight line. Sometimes I forget to change the tool. Straight line between the two. I'm not even going to necessarily connect it to the dog like that because I know what that's going to look like. So I'm just going to have the rope drawn out like that. So we have rope 1. That means that on block A, we're expecting a force like this called T1. Let me go ahead and draw my axes here. Going Y like this, going X like this. What other forces do I have on A? Well, I know there's going to be a gravitational force. Call it just MAG. That's fine. I know there's going to be a normal force. Call that an A. I also know, because there is a coefficient of friction of 0.1, that there is going to be a friction force. Call that lowercase f of A. 0.2, 0.1. So, one of the big things with this one, right? My point from before is that a rope does not really change length. A good rope is going to stay just about the same length no matter how much you pull on it. And that means that if everything is moving together, whatever acceleration sled A has, so too will sled B have that exact same acceleration. They are tied together. I shouldn't say B, I'm supposed to be writing out A here. Acceleration. The acceleration for each block should be the same. So with that in mind, let's go ahead and draw our free body diagram on what's going on with sled B. I know in the exact same way there is going to be a tension pulling me like this. It's the same T1, but it's pulling backwards now. I know there is going to be a normal force pointing up like this. I know there is going to be a gravitational force pulling down like this. I also know that I have another rope attached on the other side. Call it tension 2, like this. Finally, I have friction. Friction pulling me backwards against the motion, F of B. Is there any normal force or friction force between sleds A and B? I would say probably not unless we get into some sort of accident, right? If something happens where they collide or something else like that, but that's a very different problem at that point, right? For now, we are moving across level ground just fine, right? Clear weather, all that good stuff that I assume you need for mushing. I don't know. I've never mushed before. So, we know they should share the same acceleration. Whether or not that acceleration is 0 is not yet clear. But what we need to do here is we need to start by picking apart each of these force equations. So by now, could we just look at this and say, hey, block A, or sled A, I should rather say, the normal force of A should just be equal to ma times g. There's no other forces there. Do we all agree with that so far? Similarly, n of B is equal to mb times g. Nothing crazy going on, not a whole bunch of forces going in the y direction or anything else like that. It's just each sled has a normal force and a gravitational force. Now I will look in the x directions for each of these. I don't yet know whether or not there is an acceleration, whether it's 0 or something or anything else like that, but I do know that it will be shared between the two sleds. So I'll say whatever my net force should be, ma, should be equal to, let me look at all the forces acting on A. T1 pulls me to the right. Friction pulls me to the left. Okay? I'll fill in some of those details in just a minute here. For now, let me do the exact same thing with B, just so we can get established. T2 pulls me to the right. T1 pulls me to the left. Friction pulls me to the left. Okay. Now, let's start filling in some of these extra details. We know that these are kinetic frictions, so I can start on my left equation here and say, okay, well, whatever T1 was, that is a variable that I know, minus mu k times ma times g. So far, so good. Same deal over here. Plug in for what I've got for friction. Mu k mb times g. Keeping track of these subscripts will become very important now. Now let's go ahead and highlight the things that we know and that we don't know. Remember that in this entire thing, probably should have written this out, we are asked to find what? We are asked to find T2. So in these equations that I've got down here, let me highlight that one in purple to say, hey, this one is extra important. This is what we're really after. What other things don't I know, though? Well, I've got T1, I've got the coefficient, I've got the mass. I don't know the acceleration. I asked for that to be in red, please. Thank you. I don't know the acceleration. I don't know the acceleration, but Okay, well, I look at this now. My equation on the right, it's got the thing that I'm really after, t2, but I need acceleration first. Whether or not that is 0, I'm not sure yet. My equation over on the left-hand side can tell me that, because a is the only thing that I don't know over here. So, let's solve out for a. Acceleration should be equal to t1 over m of a minus mu k times g. I just divided both sides by m of a, and we should be able to find some sort of number with this at this point. Right? I've got 100 kilograms, all of that good stuff. I have forgotten to pull up my numbers here. That would make this a little bit easier if I had these numbers on hand, wouldn't it? So the numbers that I'm looking for in this case, I would expect to find an acceleration. What do I do with this thing? No, I set them equal to each other. Fool that I was. Well, that's all right. We can get around without solving out for this acceleration. I did this in a slightly different way. Let's calculate the thing out real fast. Let's just get a number for the sake of it. We've got 150 minus 1, or divided by 100. Subtracting from that 0.1 times 9.8. Our acceleration should be a positive 0.52. I think I jumped the gun just a little bit on some of my numbers on this one. And my solutions, I plugged that in and carried that over a little bit more before I did numbers, but that's all okay. But 0.52, if you match that, we are in good company so far. Then I go back to my other equation. I say, hey, I'm after T2. Let's go ahead and solve out for it. Let me move everything on the negative side over to the other side. So T2 is equal MBA plus T1 plus mu k MBG. Plug in all of those numbers, and what we should find at the very end of the day is that T2 should be equal to 270 newtons. Why is it T2 minus T1? Because if we go back up to our picture here, on sled B, T1 is pulling us in the negative x direction. The rope is not pushing. The rope always pulls. So, I've got one more for us here. What I'm thinking about is one last problem that's a little bit weird. Let's imagine a 4 kilogram box is on a frictionless 35-degree slope and is connected to a hanging 2 kilogram mass over a frictionless, massless, pulley by massless string, right? And I know we said a lot of massless, a lot of frictionless, but you know, it's for your benefit, I promise. When the system is released, which way will the box on the slope move? So that's an interesting one. And second, what is the tension in the string while the boxes are moving? So we don't know what direction the motion goes to begin with. You are not entirely clear whether tension is greater than or less than the force of gravity yet. But I want you to take a look at this. Drawing out your axes and determining the direction, what is positive, what is negative, is very, very, very important here. And each box will have its own set of axes. Keep that in mind, because they are different. Ropes are fantastic for that. So I want you to take the next 5 or 6 minutes, work on this one a little bit, and then we'll chat about it all together again. All right, how's about we start taking a look at this thing? So, I've got a little bit of a wonky picture here. Some variety of pieces going on in this one, and really this is going to come down to doing a lot of good stuff with our free body diagrams, right? Of course, it always comes back to the free body diagrams. We love them so much, and there's a good reason for that. So, I think I managed to extend out a thing that I did not want to, and that's going to drive me crazy, but that's something to figure out later. So we've got a slope. We've got some sort of pulley. Something like this. It is attached in some manner or another. I just like to have some of these details drawn out. However this thing would be. Something like that. Fantastic. Wonderful. A rope that hangs down that connects to a block. Look at all these wonderful pieces. We call this block 2. We also have this same rope is going to be connecting to another block that is still on the slope currently. I'm going to stick with my lines here, like this, like this, like this. Call it mass 1. Fantastic. So I don't need to split this up necessarily. My picture is going to do just fine because they are separated. I can, kind of freely draw my free body diagrams on this picture without getting them too complicated or messed up. What I am going to do is I'm going to say, hey, let me, for the sake of this, for the sake of clarity here, I'm going to draw this thing right here to say, hey, there's a pretty stark divide between these two, right? I don't want these two to be mixed together in the same way like that, because what's going on here is that on the slope, I've got some axes that I know are going to be very useful. For example, we can talk about this thing like this. Say that this is y and this is x. But when I'm thinking about what's going on with my block down here, it might be a little bit easier if I let me call this my y direction over for block 2. Question for everyone. Why would I have picked my y direction to be going down? Doesn't that go against everything that's right and just as we have seen it so far? Does it change anything? It could be where the box is heading. I'm not positive on that yet, but it is related to that point. What I have got as my x direction here, I'm doing this for clarity, but what I'm basically saying here is that if the blocks are all moving to the right, or if they're all moving to the left, I want to make sure that those directions match in some way or another. So as I've got it right now, let's pretend for a second, and let me do this thing in orange to say this is our assumption. Our assumption might be that the block goes in this direction. Let's call this A. Then block 2 should be moving down like this. That is, both of these have the exact same acceleration. The acceleration is going to be positive in both pictures. And that's just a clarity thing. Because what we would have is if we had flipped the y direction, then if our acceleration was pointing downwards for block 2, then we'd be in a situation where we would have m times negative a. Because it's the same acceleration, but what we would call positive would be different. So that's, a point to be watching out for. It doesn't have to be this way, but you have to be careful to say, hey, this is why I draw acceleration on both of these pictures. To say, hey, if acceleration goes in one way, well then the rope keeps going with it, right? Acceleration should be going this way on the other picture. So this is mostly what I'm calling my positive direction for acceleration. If I find a negative acceleration, not a big deal. That just means it's going the other way. So what do we have then? Let's go ahead and label some other things. I've got my theta right here. Let's start with block 2. That's the easier one. All of the forces that I'm going to see going on block 2 here, and I'll do these things in blue so they stick out a little bit more. I will have tension pulling up. T, I will have gravity pulling down. M2 times G. That's it. Nothing else. Block 1. I'm going to have gravity going straight down, so that's M1G. I will have a normal force going directly out, and I will have a tension pulling this way. Same tension as earlier. All right. So, and this is why, dotted lines can be useful, but here I can see, hey, it's the same rope, right? So that's kind of, my rope is like my dotted line in this case. So we know that they have to share the same acceleration. They also share the same tension. So if I were to draw out the forces going on in, let's look at block 1 first. Do I care about the y direction at all? I'll keep doing this in blue. Why not? I don't really care about the y direction. There's not friction here. Let me do this just to kind of prove my point, but because it's not going up or down or anything else like that, I know that the normal force canceled out by the component of gravity here, mg cosine of theta, but that doesn't give me any new information, and in fact, I should have written m1 right there. m1. That doesn't give me anything new, if I'm being completely honest. It's kind of useless for me. But that's not a big deal, right? You know, if we write down a useless equation, all we've done is used a little bit of extra ink. F of x, that's where stuff might be happening. So I have made a guess here that I said I think my acceleration is going this way, but I'm not sure yet. Whether it goes in the other direction, I don't know. It's not a big deal if I guess wrong, and we'll see why here. But this is kind of my process. I want to make a guess to begin with. I want to just make an assumption, and let's see if it works, and if it doesn't, then what I'm going to find is a negative answer. If it goes the other way, then acceleration is negative, and we say, okay, not a big deal. We've got the right number, just the wrong direction. So I look at all my forces going in the x direction. I have the tension is pulling me to the right, and I have the x component of gravity pulling me to the left. Perfect. Well, let's think about this here. Think about the pieces that we're after. We're after the tension. We're also looking for what direction is acceleration going. Was our guess correct? Solving for tension, though, is really, if I can find out tension, I can solve the rest of this. We'll figure out the direction kind of as a step along the way. I look at my variables that I know and that I don't know. I don't know acceleration. That is something that I'm certainly after. I don't know the tension. That is also something that I'm certainly after. Yikes. Go ahead and write some of these things down while we've got it in our mind. We're given theta is equal to 35. Mass 1, this was our 4 kilograms. Mass 2 is our 2 kilograms. Okay, so 2 unknowns, I can't do much with that. And let me go ahead and extend out this layer a little bit to say, hey, you know, here's our divide still, right? That's where our divide is going. Don't mix these two sides quite yet. They share some variables, but our axes are very different. We're talking about each block individually. So then, let me think about what's going on with block 2. This one's a little bit easier. I would say that here, in my y direction, I have guessed that acceleration is going in the positive y direction, as I have it labeled. Then I would say, okay, well then gravity points in the positive direction, tension points against that. Same deal, I highlight the things that I don't know, and wouldn't you know it, it's the exact same 2 variables that I didn't know in the other part. So now we're going to start to combine some of these details together, right? So let me get rid of this divide so that we can have some sort of connection between the two. So I'll do this in a new color to say, hey, we're trying to take these 2 things and slap them together in some way or another. I'm interested in acceleration, right? I need to know what direction this thing is going. So before I do that, let me take this one step back. Let me go ahead and solve out for the tension. Tension should be equal to M2G minus M2A. Something just like that. Okay, now let's take this thing together. What we end up getting, M1A, plug in what we just found for tension, minus M1G sine of theta. Okay? Remember that we are after our acceleration here. So let's group that together. I'm going to group it all together on the left-hand side. Simplify it a little bit. Now I've got M2G minus M1G sine of theta. My acceleration is this slightly nasty thing. Divided by M1 plus M2. So, when we slap all of these things together, what we should find at the end of the day is... Yikes! Negative! Oh no! Negative 0.481 meters per second squared. What happened? Is it a big deal? Not really. I don't see anything wrong with this. What this negative sign means is that the direction that we have guessed is incorrect. I guessed that block 2 was going down and block 1 was going to the right, up the slope. I was wrong. I got a negative answer. Whatever direction we had just guessed for our acceleration, it's actually going in the opposite direction. But the number doesn't change. That's the beauty of being able to decide our axes like this. It doesn't matter, right? We get a negative sign somewhere else that we wouldn't have otherwise, but if we had flipped the axes in the first place, or if we'd flipped the acceleration in the first place, then we'd have negative signs everywhere else too. What we have just found is that our guess was wrong, but by making a guess and sticking with it the entire time, we have stumbled upon the correct answer anyways. That's our process here. We can make a guess to begin with, and it's not a big deal. What I can't do is say that the block is going up the slope and the mass that's hanging over is also going up. I can't do that because now I've got kind of a contradiction, right? There's no way it can be both at the same time, so I've got to just pick one direction one way or the other. I take a guess, I go with it. We see what happens. In this case, my guess was wrong, but we found the right answer at the end of the day anyways. We were corrected. We know that everything is sliding to the left and sliding up. How do we feel about that? Any pitchforks or anything else, or are we feeling all right with this idea that, it's totally all right to make a wrong guess? How do we go about choosing the axes for our objects? Same kind of deal, actually. Guess. It's not a huge deal. It's not a huge deal for any of these things. For the question, wouldn't it be easier to find the net force first? You run into an issue of we don't know what the net force is because in both cases, we don't know what the net force is because we don't know what tension is. There's no way to solve out for either net force first. So the net forces don't necessarily have anything to do with each other. The accelerations do, though. So that's why I immediately want to jump to MA. The net forces are just kind of like a stepping stone for me. Could we know that the mass of block 1 would have been, the bigger one that's causing a little bit more stuff going on? Not necessarily. The direction was not necessarily clear from that, because if the angle was any different, actually, in fact, if the angle was 30 degrees, the acceleration would be 0. It depends on the angle, it depends on the relative masses. So I wouldn't necessarily know this right from the start. And that is one of the dangerous things. Sometimes I do know some variables, whether they're 0 or something else like that, but oftentimes I have to make a guess and I have to be ready to say, hey, that guess was wrong, and that's not a big deal. Our guess was wrong. Block 2 goes up. But one of the big deals at this point is I want to change nothing. Do not change any of these values. I have already set what everything is going to be. I need to stick with this number the entire time. When I go back up into these higher parts here, if I want to find that tension, if we had flipped our axes, then yes, we would find a positive 0.48. But what I need to do with this value now is I can go back up. I'm looking for the tension as my last little bit of detail here. So let me take my mass 1 acceleration is equal to t minus m1 g sine of theta. Do not plug in positive 0.481. We have set our picture. We drew the picture like this. We have made our decisions. We have to live with that through the end of the problem. We have already decided how everything is going to be laid out. So what I need to do now is when I plug in these numbers, this needs to be mass 1 times negative 0.481 is equal, well, let me just go ahead and move over. You cannot flip your direction halfway through the problem. You make a decision, you stick with it to the very, very, very end. Right? This hand-wavy description, our guess was wrong and the block 2 moves up, is not changing any of the numbers. We leave acceleration exactly as it is. We don't try to fix it now. It's too late. And it's not a big deal that we guessed wrong in the first place. But we just need to keep that number going because that number, this negative 0.481, was the same number that has permeated through the rest of the problem up until this point. So to change it to be a positive now is to just flip a sign for no reason. But when we plug all of this stuff in, what we will find at the very end of the day, if we're looking for that force, is 20.56 newtons. $19.6. I'm not sure where that would come from. It shouldn't be 19.6. It shouldn't be 19.6. Because 19.6 implies that your acceleration is 0. mg is not equal to t. mg does not equal t. mg would only equal t if there was no acceleration. Right? We go back to the this picture right here. If there is an acceleration, that means the forces are not balanced. If the forces are not balanced, then tension is not equal to gravity. If tension is not equal to gravity, there's a couple different ways that we could think about this, right? But what it's basically saying here is that they're just not going to be equal. Don't assume that the acceleration is 0. Whether it's larger or smaller is not a really big deal, but just don't necessarily assume that they are equal to each other. Okay. For now, what I'm going to say, just for kind of the sake of the populace at whole, there is no reading due tonight or anything else like that. I've only got so much cruelty built up inside of me. I can't inflict it constantly quite like that. So no reading tonight. The in-class questions, hopefully a little bit more casual, a little bit more smooth this time around. There is a homework with all of this stuff, of course. There's always going to be some homework. But that's all the material that we've got today. We will be approaching Chapter 8 next time, and a reading will be released for that one quite soon here. So, for now, though, that's, to release everyone who was looking for the end of the course and everything else, or the end of the class at least, not the course.